will briefly go over a couple of additional features that I present in both VCell and Capacity. I will show things off on the VCell side and Stefan on the Capacity side, which deal with different ways of simulating a same model other than deterministic simulations, which you've seen so far, whether or not they're compartmental or spatial. And I will focus on compartmental stochastic simulations. The spatial stochastic simulations will be introduced tomorrow, and which is one part. And the other part is related to having moments in time defined in the system where things may suddenly change. Let's say you are stimulating or inhibiting or applying some process that creates a discontinuity in how the system behaves at that time. So I'll turn off my video and share my screen. Okay. Everybody see my screen?
Yes.
Yes.
Okay. So I will use some very simple examples for this based on the same sort of token model that I've shown yesterday to introduce spatial simulations. And we're talking about the simple phosphorylation reactions where we would have a substrate and a phosphorylated substrate and an enzyme where the reaction of phosphorylation is catalyzed by the enzyme according to some standard enzymatic kinetics like Michaelis-Menten, where we have some Km and the Vmax is dependent on the actual enzyme. And let's give this a value. And we have seen that this system can be simulated deterministically in a very simple way. We initialize, let's say, let's use more reasonable concentration for proteins like 100 nanomolar for the substrate and maybe 15 nanomolar for the enzyme, and simulate this for 10 seconds. And okay, what did I miss initializing here? Substrate simulations reaction. Let's try this again. Maybe there's a bug. Oh, I did not initialize the enzyme. So now let's assume this is happening in a small volume where the number of molecules may not be that large. And because of fluctuations in noise, some of these processes that are represented by differential equations may not actually correctly approximate the reality of the fact. And you can run the exact same model using a stochastic solver by just creating a stochastic application. And when you copy the deterministic application into a stochastic application, under the specification, you will see that you have the initial condition of the species can be displayed in two different ways: the standard way of providing a concentration, or as a number of particles. So you can see that in the default volume with these concentrations that I've used, the number of protein molecules of substrate and the number of enzyme molecules is fairly large. So if we would simulate this in a stochastic way, basically you don't see anything sort of different than in the deterministic, because given the large number of molecules, the deterministic system of differential equations is a perfect approximation of what actually happens with the individual molecules interacting. One other thing to point out is that in the display screen of results from stochastic application, again, you will have two ways of displaying your results, either as a concentration or as an actual count of molecules. Okay, now what if the same reaction would actually happen, not in the volume of a large eukaryotic cell at 50,000 cubic micron, but maybe in one small bacterial bacterial cell that's approximately 1 cubic micron in size. And if we simulate this again, let's try this again. Now you will see that both in the enzyme and substrate, you have sort of a stepwise change, which we can further explore by looking at the smaller time sequence. And you could see that at this point, it actually dropped to 0. That's actual true 0. And then it won't change from 0. So it's no longer a nice sort of tangential going down to lower and lower concentration, because if you go beyond actually one molecule, you get to 0, and that's it. So there's no such thing as 0.1 molecules. This can get a lot more complicated and have significant effects on your system, which you can take a look at the tutorial application. I can show you a public model of a circadian cycle in bacteria that is where you can illustrate the actual effects of these stochastic interactions. For example, where this is an oscillatory model which, oops, cell is not cooperating right now. Where you see that the actual oscillations are not uniform in size or amplitude. And if you further explore the parameter space of the model, you will see that certain changes in parameters which do not do eliminate oscillations in the deterministic approximation, do not in the stochastic approximation. So the entire behavior of the system can go way beyond just a noisy display of your data, but to qualitatively completely different applications. Again, if we're talking about tens of thousands of molecules, there's no point in using stochastic simulations that are slower and much more computationally intensive. But if you're dealing with small number of molecules, you may or you should run your simulations using stochastic numerical solvers. And the last part, which I'm only going to take a minute on, let's go back to this model, is that sometimes you will need during modeling to introduce changes that occur during the course of the simulations. And maybe this enzyme is only activated at a certain time point, which you can describe it like saying the enzyme gets activated only after 5 seconds, so when time is greater than 5 seconds. But that has certain limitations and is not, really the best way to describe what happens at different time points. A much more powerful way of doing that is with defining so-called events. And we can define an event, let's say at a single time point, at time point 0.5, or when a certain variable exceeds a value or goes below a value, or at different times when you want to apply simulation. There's a number of different predefined trigger conditions. And so that tells the system when is the discontinuity, the change being introduced. And then on the bottom, you will define what happens. So you will say that maybe at that point, we can add an action where we can modify the enzyme and say it got maybe inactivated. Now it's 0 after 5 seconds. And all you have to do is to just simply rerun this model, and you will see that your phosphorylation of the species is happening for the first half of a second, and then it stops because we set the enzyme to 0. So this is, again, only scratching below the surface about what you can do with stochastic simulations and introducing events during the time course of the simulation.